This is a tutorial to investigate the discrete time simulation for the binary counter problem. Now, when I presented this in lecture, I described the binary counter problem with a transition and output table. Now, similar to the previous tutorial looking at the delay system case, this has 4 columns: the current output, the current input, x of t, the current state, q of t, the next state, q of t plus 1, and the current output, y of t. Now, this transition and output table describes all of the different possible cases that we could encounter and describes how the next state and output should be handled in each of these cases. So in the binary counter problem, we have a system component that has one input, x of t. It has some state, q of t, and it produces an output, y of t. And if the inputs and state are constrained to binary values, 0 or 1, there's 4 conditions to consider. Input 0, state 0, input 1, state 0, input 0, state 1, and input 1, state 1. These are the 4 possible situations that we have to define rules for the binary counter system. So in this particular case, we have defined in lecture that if we have input 0 and state 0, then the next state should be 0 and the current output should be 0. So if we have a system that has a current value of 0 and it has an input value of 0, we've defined it to be current output of 0, and at the next time step, we want it to have a next state of 0. Got a nice little line here across my screen. Okay. So we can continue and define similar types of functions for the other cases. So for example, if there's a current input 1 in the state of 0, then the binary counter defines that the next state should be 1 and the current output should be 0. So this is a definition for input 1, state 0, output should be 0, but the next time step should be 1. Right, the state at the next time step should be 1. And similarly for the other two cases, we define if the input 0 and the state is 1, then the next state is 1 and the output is 0. So if we have 0 input but 1 state, then the current output is 0, but the next state should remain at 1. And input 1, state 1, define that the next state returns to 0, and the current output should be 1. So 1 input, 1 state yields current output of 1, and the next time step it should revert back to 0 state. So these transition and output rules can also be defined in a mathematical form. We've been using in class the notation of a delta function, which could be a function of q and x for the next state. And in this particular problem, we can use a logical function, exclusive or XOR. So q, x, or x. What this function does is if either q is 1 or x is 1, it returns 1. But if both q and x are 0, or if both q and x are 1, then it returns 0. So we can see that those cases are exactly represented here. If q and x are 0 or 1, it returns 0. If either q or x are 1, then it returns 1. Similarly, to define the output function, we've been using the notation lambda, which could be a function of q and x. And in this particular case, we can express this with a logical function and, q and x. So if both q and x are 1, then we get 1 as the output. Otherwise, in the other 3 cases, where neither q and x are both 1, then we get 0. So using the transition output table, or equivalently the transition or the output function, we can then plot out the effects of a discrete time simulation. So for a similar case for the delay system, if we consider over time with a few time steps, 0, 1, 2, 3, 4, we can define an input trajectory, x of t, and let's just say that it's an alternating input trajectory again that alternates between 1 and 0, right? So it's a pulse, on, off, on, off. So given this particular input trajectory, then we can, and also an initial state, let's say that our, our model starts in state 0 times 0. We can figure out what the next state is. So if we have 1 input and 0 state, following the transition table, 1 input, 0 state, our next state is 1. Right? Similarly, if we have 0 input and 1 state, 0 input, 1 state, our next state is 1. 1 state, or 1 input, 1 state, here we go, 1 input, 1 state, our next state is 0. And 0 input, 0 state, our next state is 0. The last piece from this is we can represent the outputs, y of t. So using the same time steps, 0, 1, 2, 3, 4. We can follow the output rule. So for 1 input, 0 state, 1 input, 0 state, we have 0 output. For 0 input, 1 state, here we are, 0 input, 1 state, 0 output. But for 1 input, 1 state, here's this one condition, 1 input, 1 state, we get 1 out for the output. Right, and we could follow a similar logic to get the rest of the results for this particular simulation. Now this is called a binary counter because what this output is actually doing is counting up the number of, or it returns a 1 every time there's been a multiple of 2 inputs that have been logged at some point in the past. So here we can see that there was one previous input that was recorded at time 0, and in this case the second input was recorded at time 2 when the output then returned a positive, or a value of 1, and then it resets.